In the first problem, we have potential gravitational energy and kinetic energy. And we also know we only use 80% of the total energy, since we lost 20% of this energy in friction. So the first step is to equate the energies and also multiply the potential gravitational energy times 0.8, since it represents 80%. Then we can start solving. We can cancel mass and also multiply 10, that is our height, times 0.8. So we are left with 8 times gravity equals 1/2 times velocity squared. We are looking for velocity, so we pass the 1/2 multiplying, and now we have 16 times gravity equals velocity squared. And now we only have to get the square root of 16 times gravity, and if we simplify this, we are left with 4 times the square root of gravity.
First, we have that the constant of the spring is equal to 200 newtons per meter, and that the initial extension of the spring is equal to 3 centimeters, or 0.03 meters, and the final extension is equal to 0.05 meters. Then we calculate the elastic potential energy for both cases, and we subtract the initial elastic potential energy from the final one to get the total work done, which is equal to 0.16 joules.
First of all, we have to know our data. We're at 2 kilogram boxes moving 5.4 meters over seconds over a 4 meter distance. First of all, we have to know that the change of energy is equal to the work, and we have to know the work to get the friction force. So the change in energy would be the final energy minus the initial energy, and the final energy would be equal to 0 as it comes to rest, minus the initial kinetic energy. This energy should give us 33 by substituting all the data that we have, because 1 times the mass times velocity squared over 4 cosine is 1.80.
To get the final kinetic energy of the object after 50 meters. So first we look at the provided graph, and we see that it's a force and distance graph, and we know that force and distance is equal to work. So we can see that the triangles will represent the work done. We can see that the base is 5 and the height is 80, so we just use the triangle formula to get the area of the triangle, and we multiply it by 3 because there are 3 triangles, and we get that the work is equal to 600 joules. However, we know that there is an opposing force of 2 newtons acting on the object, so we have to get this work by the opposing force. We just multiply the 2 newtons by the 50 meters and cosine of 180 degrees, because we know it's opposing motion. So if we compare this work, we get 600 minus 100 is equal to 500 joules. This will be our work net, and we know that our work net is equal to our kinetic energy. So now we know that the kinetic energy is equal to 500 joules.
In the fifth problem, we have that a ball undergoes an elastic collision with a vertical wall. So, which of the following statements is equal to 0? The options are A. The change of the magnitude of linear momentum of the ball. B. The magnitude of the change of linear momentum of the ball. C. The rate of change of linear momentum of the ball. And D. The impulse of the force on the ball. So to solve this, we only have to take into consideration that the only thing that changed was the direction. So the momentum did not change. With this in mind, the only option that is correct is A. The change of the magnitude of linear momentum of the ball.
First, we have that the constant of the spring is equal to 200 newtons per meter, and that the initial extension of the spring is equal to 3 centimeters, or 0.03 meters, and the final extension is equal to 0.05 meters. Then, we calculate the elastic potential energy for both cases, and we subtract the initial elastic potential energy from the final one to get the total work done, which is equal to 0.16 joules. First, for part A, we find the speed of the ball just before the collision using conservation of mechanical energy. The ball is released from rest when the string is horizontal. When the string becomes vertical, the center of the mass has dropped a vertical distance equal to the length of the string, which is 0.95 meters. So the change in the height is h equals 0.95 meters. Since tension does no work, mechanical energy is conserved. The initial energy is gravitational potential energy, and the final energy is kinetic energy. The mass cancels, and solving from uv and substituting our values, we get that velocity is equal to 4.32 meters over seconds. So the speed of the ball just before the collision is approximately 4 to 32 meters per second. Now, for part B, we prove that collision is elastic using kinetic energy. Before the collision, the ball has a speed of 4.32 meters over second, and the block is at rest. After the collision, we are told the block moves at 2.16 meters per second. First, we find the velocity of the ball using conservation of linear momentum in the horizontal direction. Now, substituting the values and solving for the velocity, we get that the velocity equals minus 2.16 meters over second. The negative sign shows the ball rebounds. Now, we compare kinetic energy. For the initial kinetic energy, after substituting the initial velocity, we get that is equal to 7.47 joules. Now, the final kinetic energy, if we substitute both velocities, we get that is equal to 7.47 joules. Since the total kinetic energy before and after the collision is the same, kinetic energy is conserved. Therefore, the collision is elastic.
One problem to ask to solve is to find the kinetic energy of a ball that does not stop. We can use this part of the problem as before how to go, so we must use reasoning. And to find the kinetic energy, we should add all the energy that we have and start substitute with the value. Also, the mass of the ball it would be 2.7 kilograms as we do 2.7 kilograms the weight of it. So we have to add it in kilograms. So let's put 8. Let's substitute what we have. So as I told before, 2.7 over 1,000 times gravity times height of the ball, same thing that I just told. And the velocity is still 1.15. squared, and the result would be 0.36 joules. That is our kinetic energy. The second part of our problem tells us the player B intercepts the ball at its speed high. Calculate the average force exerted by the ball in the paddle. So this part would be really easy as it's basically the theory. We have the ball that goes before and the after. The only thing that happened is that it changed back. It has the same energy. So if this was simple, but the problem is to forget we have to find the force. The force is equal to the change of energy over the change of time. We know that the time there was 0.0 and notice minus 10.15 minus over it's our 5.67. For our third problem, we have a 4.2 kilogram box moving through this type of ram, if you want to call it for some name, with 5.6 meters per second. The ram has a height of 0.85 meters and it has a distance of 2,000. We have to compare the kinetic energy to the potential rotational energy that we have plus the elasticity that we have. Thus, we know how much it compresses the spin. So it's simple. First of all, we have our very nice formula. So we have to compare. Then we can wrap it up with by moving this x by the side and moving all the things. So we have that x would be equal to 2 and half plus this one. And with simple substitution of all the data that we have here, we can get how much we compress. That is 0.529 meters.
For B, we're asked the same but now with friction, and now we know that the path is 1.2 meters long. So first we have to get the work of the frictional force, and after getting the work of the frictional force, we only have to add the kinetic energy and equate it to the potential rotational energy plus the elastic energy, and we have to do the same process for getting x. After solving, we have to get 0.3466